welcome back friends. In the previous lecture, we had introduced you to the various concepts in capacity and speed calculations of bus and rail transit. In this lecture, what we are going to do is show you some solved examples of capacity and of capacity basically of rail and bus transport, so that this will help you understand those theoretical concepts that you have already learned in the previous lecture. We are going to give you one example each how to determine bus capacity and rail capacity, and mostly what you will see are empirical formulas that are used in understanding or in calculating these problems. So, you do not have to worry about memorizing these formulas, but understand the concept of what are the different inputs that are needed in these calculations, and if you understand those, the rest is pretty simple. So, if we start with the first problem where we are trying to determine the bus stop capacity. So, as you see, finally, what we need to determine is the bus stop capacity. So, say Kolkata, which is a central city in eastern India, is examining opportunities to improve transit service through its downtown core as part of a downtown circulation plan. Existing bus service to the downtown is concentrated on say a street X, which is a one way route just over about 5 kilometers in length and has 4 bus stops. Okay. It has 2 through lanes with on street parking provided on both sides of the street. The route is served by 6 different transit routes. Okay. So, along this 5 kilometer stretch there are 6 different transit routes operated by say a fictitious agency called Kolkata City Transit with combined peak hour frequency of 26 buses per hour. That is a combined frequency of all the 6 routes combined. Buses stop every block with an average block length of 1.2 kilometers. On street parking is removed at bus stops to allow buses to access the curb, and buses must exit the traffic stream to serve the passengers. Traffic signals are located at each intersection along the downtown street. So, this gives you the understanding of the existing situation, right. So, this is a common existence in any of the cities, towns where you may have a bus route or a bus network or a bus system. You will have certain bus routes, certain overlapping bus routes, they will have certain designated bus stops, they may or may not have on street parking, right, and traffic signals may or may not be there. So, in this case everything is given to you, and what you are asked to calculate is first calculate the average dwell time, second calculate the loading area capacity, and finally using these to calculate the bus stop capacity, right. And we have learnt about all these theoretical concepts in the previous lectures. So, just go back and look at the definitions of all of this, and then you will follow through the example problems. So, now let us first look at the inputs that will be needed to calculate each of these 3 parameters. So, inputs needed to the problems are say, so we know that there are 4 stops along that line. So, for each of the stops what you will need is average boarding volume per bus, average alighting volume per bus, how many boarding doors are there or where they are there, right. Are they in the front, or is boarding allowed only through the front door or back doors or both doors. So, where are the boarding doors? What is the fare payment method? Is it exact change only, right, or is it say for example smart card, is it a single ticket token. So, what is it, what type of fare collection is operating in your bus system, that you have to know. Boarding height, whether your platform is at level with the bus landing or is there a difference. Standees present or absent. So, do you allow standees on the bus or not, or only sitting is allowed. Number of doors, available door channels. So, door channels meaning if it is a 2 door that opens into the bus, then the 2 door will have 2 channels, although it will be considered as one boarding gate or boarding door, but it will have 2 panels, right. So, if 2 panels open up, that means 2 rows are formed. So, it is one door, but now there are 2 channels, right. So, that is what is known as channels. Percentage of boarders using fare box. There may be some lot of persons who have daily passes, or they do not need tickets. So, there will be only a portion of them who will need tickets. So, what is the percentage of people who actually uses the fare box that is in the bus? Now, you would be thinking that realistically in many of our or most of our buses there is no fare box kind of a system, but think about it as a these modern POS machines, right, POS machines. So, there may be POS machines through which you can buy a ticket. There may be, if you have a pass, then you just show a pass. If you are a student, if you are a elderly citizen, say for example, maybe the bus ride is free for you. If you are a woman in Delhi, maybe the bus ride is free for you. So, all of those factors act in this calculation of the dwelling time at a stop, right. So, you understand, you remember what is a dwelling time? Dwelling time is the amount of time a bus is stationary at a stop to pick up and drop off passengers, right. So, all of these factors that we are talking about goes into the calculation. They are all inputs. They go into the calculation of the dwelling time. Last two ones are door opening and closing time. So, there may be some few seconds that go into the door opening and closing, and the number of loading areas. So, remember a bus stop may have only one loading area, or it may have sometimes two loading areas back to back, right. So, there may be one or two loading areas. So, these are all the inputs that are needed. Then you will have some default values that you can use, right. These default values have been developed by looking at various bus systems across the world. So, these are average values or best practices values. So, whatever they are some kind of default values which will allow you to at least get started with understanding what how your bus system capacity works or what is the dwelling time. So, there are some of these fare payment types times, right. So, these are number of people, number of seconds per person, right, as seconds per person, how much time is needed to process the payment of one person or one passenger who is entering the who is boarding the bus, right. So, seconds per person or seconds per passenger, whatever you may think. So, you will see there are different types of different times that are given as default values. So, based on what type of fare payment method your bus system is operating on, you may assume or you may select any one of these two values, right. So, alighting times are also some standard values for alighting times are also given. These are fare payment times and these are alighting times. Okay. So, this is what some standard values. Like I said, these are all empirical studies that have been done across the world, and these values or this formulas also that you will see, they are all developed based on these empirical studies that have been carried out. So, first what you would like to do is you will have to calculate the number of boarding and alighting passengers through each door channel, right. So, remember it is not the door, but the door channels. If like we discussed, one door has two panels, that may create two channels, right. So, in order to do so, I will just go through the calculation for one stop, and you may do the similar calculations for all the other stops, but anyhow the answers are showed here, just follow through these answers. So, if you want to calculate, for example, what is called PB1, which is the boarding passengers through door channel 1. Okay. So, what you have to do is average boarding volume per bus multiplied by the percentage of boarders using fare box. Okay. So, now these two values are already been given to you as input parameters. For example, average boarding volume per bus in stop 1, you know, as average boarding volume per bus is 3 in stop 1. So, there are 3 people on an average that board or this bus from stop number 1. So, you multiply that by the percentage of boarders using fare box. So, the percentage of boarders using fare box, again it has already been given here, which is 45%. So, if you multiply 3 times 0.45, what you will get is 1.4, right. So, you do all those for every other stop. You will see some of the stops have 0 values or no values, that is because no passenger is allowed to board through door channel 3, or no passenger is allowed to alight through door channel 1. So, there may be some restrictions So, if there is nobody allowed to board or alight through one of those door channels, then there is no in the calculation of the number of people boarding and alighting, that value will be 0. Okay? Simple enough. In similarly, while calculating the number of passengers alighting through door channels 1, well, 1 values are 0. So, if you do it for door channel 2 for bus stop 1, all you need to do is average alighting volume per bus times 0.25. Now, again 0.25 is a standard number that is assumed for alighting, right, and those alighting times are given here. These alighting times, average alighting volume, you know the average alighting volume, right, you know the average alighting volume. So, multiply the average alighting volume by 0.25, you will get these numbers. And if you just want to do the next number, so P A 3, so average alighting through door channel 3, because you know the total average alighting volume, that is you know 3. So, 3 minus 0.8 essentially is 2.3. So, I think it is rounded off to the 1 decimal, that is why it has to be 2. I think this 0.8 is 0.75 or something like that. So, they are rounded off. So, do not worry about the rounding off. So, these are simple calculations for the first step, which you have to calculate to determine the number of boarding and alighting passengers through each door channel. Next, you have to calculate the boarding and alighting times through each channel, right. Now, you know how many people are boarding and alighting through one channel. Now, you need to know the time that people are using to board or alight. So, again similarly all the calculations for all the 4 stops are shown. Let me just take you through one stop. So, if you have to calculate TB1, that is the average boarding service time for door channel number 1, all you need to do is time taken for fare payment exact change is equal to 4.5 seconds, no alighting through board. So, this is the time taken to board through channel 1, as there is no alighting allowed through channel 1. So, it will be only the time that is needed by people to board, and we already know that that time is equal to the time taken for fare payment in case of exact change. So, this since we have already shown that these are using exact change. So, as in case of exact change here, in case of exact change right here, we know that the time taken for exact change is 4.5 seconds. So, time taken average boarding service time through channel number 1 for stop 1 is 4.5 seconds. So, it is as simple as that. If in case for channel number 2, for example, where both boarding and alighting are allowed, right, these are door channel number 2 where both boarding and alighting time are allowed, you have to multiply this time taken for visual inspection into 1.2, right, because now you are visually inspecting who is boarding, who is alighting. So, that adds a little bit of time to it. So, you know what is the time taken for visual inspection, that is 2 seconds, 2 seconds per passenger, you multiply that by 1.2, right, and you will know what is the time taken. After you have calculated now this time taken for boarding and alighting, next what you have to do is you have to calculate the passenger flow time through each of the door channels. Now, you know the number of passengers, right, you have calculated the boarding number of passengers, and you have calculated the average boarding service time. Now, you have to know the passenger flow time. So, all you have to do for passenger flow time is you have to multiply the number of passengers boarding through each channel times the number of times the time taken for them to board, and you have to sum all of those for all the different channels that are available. So, it is just a summation of the product of P A times T A, right. So, whatever if you do T, so T is equal to A to N. So, how many hour channels are there, you develop the product of it and sum it. Okay. That will give you each of these values. So, that gives you the passenger flow for each of the door channels. Now you know the passenger flow through each of the door channels. In order to determine your first answer, which is average dwell time, now you have to, all you have to calculate is, you already know the passenger flow, which you have calculated in the last one. Boarding loss time is something that again is a standard value that are given. If there are only one loading area, there is no loss. If there are two loading areas, there is a 2-second loss, because you know, if there are two loading areas back to back, so the bus that is coming behind sometimes faces a little bit of delay if the bus in front is not parked properly. So, there will be a slight delay if there are two loading areas. So, stop 3 and stop 4 has two loading areas. So, that is kind of a boarding loss time, and already the door opening and closing times are given to you as standards here, door opening and closing times right here. So, you take these two times, two time factors, and you take and you already know the maximum passenger flow time, then you add up all the 3 times. If you add up all the 3 times, this tells you that this much time is needed to process the passengers boarding and alighting, because there will be people paying ticket fares and so on and so forth. So, that gives you the total time needed for that. This gives you the boarding loss time in case there are loading areas, multiple loading areas, and this gives you the door opening and closing time. So, that will give you the average dwell time for each of the stops, right. So, that solves our first problem. For the next problem, which you have to calculate the loading area capacity, again there are a bunch of inputs that are needed, and these inputs are shown here again. Inputs are green time ratio. Now, loading area capacity depends is influenced by, if the bus stop is near the intersection, then the green signal at the intersection affects the loading area capacity. So, you have to know the green time ratio, the traffic signal cycle length, what type of stop it is it in online, or does it have a bus bay, and so on and so forth, which area it is it in a CBD, non-CBD, or some other type of area, residential area, so on and so forth. You have to know the which area the bus stop is in. Then you have to know the curb lane traffic volume, curb lane only, right. If there are multiple lanes, all you have to know is the traffic volume on the curb side lane. The right turning volume, in our case the left turning volume, that is because we have free left. So, those vehicles turning left may affect the loading area capacity of the buses. So, since this example is taken from example in the United States, they have right turning volume conflicts, we have left turning volume conflicts. So, in our case this will be left turning volume. Conflicting pedestrian volume. So, at the intersection there may be pedestrians who are trying to cross, and the bus is also trying to go through. So, there or turn left. So, there may be some conflicts there. That arrival types of the buses, do they arrive in a platoon, together bunched, or do they arrive in a random fashion, number of physical loading areas, which you already know, loading area design, and the bus lane type. All these have to be input parameters have to be known. Some of these input parameters will have standard values, which will come along with these known parameters, and once you know that, you can start calculating this. The first step in calculation of loading area capacity is the calculation of the clearance time. So, in calculation of the clearance time, you need to calculate 3 different parameters. One is the re-entry movement capacity, re-entry delay, and the other is a queue service delay. Now, do not get caught up in the complexity of the formulas. The formulas are very empirical. They are each of the values for each of them are given. All you have to understand is what is happening in this case, right. Since you are trying to calculate the loading area capacity, the loading areas may be 1 or 2. So, what the loading area capacity depends upon is the re-entry movement capacity. So, since these buses are stopped at the loading area, if they cannot re-enter the traffic lane, then the next bus cannot come into the loading area. So, the re-entry movement capacity affects the capacity of the loading area. A re-entry delay, so from capacity you can calculate the delay, right, and then queue service delay. So, now if there are queues formed of buses that are wanting to come into the loading area, those queue. So, the queue service delay, the delay due to the queuing system for these buses is also calculated in order to determine the clearance time. That is the first thing in understanding or in calculation of loading area capacity. Again, these are all shown for 4 different stops. Let us go through one of these stops and say that re-entry movement capacity. So, the first calculation of re-entry movement capacity only depends upon your volume of vehicle on the what you call the curve lane, volume of traffic volume on the curve lane, VCL, right, VCL times e to the power minus VCL into TCH. TCH is nothing but the critical headway for re-entry movements. Again, standard values are given there, right. This is re-entry in seconds. So, you have to convert it into hours, I guess, and then divided by 1 minus VCL times TF. TF is the follow up time for re-entry movement, again that is given. So, you just enter those values, you get the re-entry movement capacity. From the capacity you can calculate the delay. All the terminologies are already explained here. These are NLA is the number of lanes, and everything CRE is something that you already calculated here. You insert those values, you get a re-entry delay, and from the re-entry delay what you from the re-entry delay what you need to calculate. After the re-entry delay what you need to calculate is queue service delay. Again, queue service delay depends upon QR, which is the queue size at the end of the effective red time. So, there may be the signal has a red time, even after the red time there are n number of people that number of vehicles that are queued up. That means the green time was not able to service all these vehicles. So, there was a queue formed. So, that queue service delay here is calculated. Again, you see the G by C ratio, you already know the green time ratio right here, you know the capacity, you know the volume, you know the volume of the curved side lane. So, all of these are already known. You calculate these. So, you know now you have calculated your re-entry capacity, you have calculated re-entry delay, now you have calculated your queue service delay. There is something called a re-entry delay for case 3, where case 3 is influenced by the signal nearer the far side. So, it is again an assumption whether it is influenced or not, and standard values are again given here. You assume those. Startup time, time needed to if you are stuck in the queue and you want to start back up, those are standard values that have to be inserted in, and then clearance time is nothing but your TSU plus delay terms. So, TSU plus delay. So, you add up these and you get your, or you add up these two, you get your clearance time values. So, now that you have your clearance time, your bus stop capacity calculations can begin. Before you do your bus stop capacity, we are doing your loading area capacity. So, loading area capacity, you bring in all these input values that are already been calculated, green time ratio, you know, coefficient of variation of dwelling times, you know the dwell times from numerical 1. So, you bring them in here, you calculate what are the what is the coefficient of variation in each of those dwelling times, and you put it in there, right. You know how to calculate the coefficient of variance of any given data set. Then along with that, you know what is the failure rate. Failure rate, a standard failure rate can be assumed here as well. Failure rate meaning every time the bus is unable to get re-enter back into the stream. So, there may be certain percentage of time because of the queuing, because of the queues formed on the travel lane, it is not able to re-enter. So, you can calculate the failure rate, and from the failure rate you can do the corresponding, say that the failure rates are normally distributed, then you can calculate the corresponding standard normal variables for the failure rate. So, 15% times it fails, that means 85% of the times it is able to get in. So, for a standard normal, if you go and look at the Z curve, what is called the Z curve, then you can find these normal values of 1.04. In case of 25%, there will be 75% times it is able to enter. So, that values will be different. So, you know all of those. Operating margins are something that are standard let me see if I am able to give it here. Those are operating margins are also okay. Operating margin calculations is given here. So, operating margin calculation is nothing but the coefficient of variance in dwell times multiplied by the standard normal multiplied by T d, where T d is the average dwelling time, which you have already calculated in problem 1. So, if you just multiply those, you will get the operating margin, and then you know from the operating margin you can calculate the loading area capacity with this formula. Again, this is G by C ratio you already know, T c you already have been given, T d you have already calculated, G by C you know, T o m is the operating margin that you have calculated. So, using that you develop the loading area capacity. So, now you have calculated dwell time, you have calculated loading area capacity. Based on this loading area capacity, you can determine what are the number of effective loading areas. So, if you have one loading area, the efficiency is usually 100%. So, effective loading areas are 1. If you have 2 loading areas, the efficiency is 75%. So, the cumulative effect is 1.75. So, these are again standard tables that are available for you for online loading areas versus offline loading areas. So, you can input those values again. Why are we inputting those values? Because finally, we want to calculate the bus stop capacity. Lot of the all of these calculations in bus stop capacity are already, many of them have already been developed because we are going sequentially from one problem to the other problem, right. So, you know already what is the curb lane traffic volume, you know the right turn lane volume, in our case the left turn lane volume, pedestrian volume you already know, arrival type you already know, stop location has been determined, TOM we just calculated, loading area design we just calculated, right. Effective loading areas also we know. Now, in order to calculate the bus stop location factor FL, bus stop location factor again is given by a standard table. These standard tables tell you that if it is a lane use a lane type versus bus stop location, if it is a near side type 1, then you can use this one, if it is a near side type 2, then you can use these values. So, we all put in whatever value it is, that means this is a far side lane type 2 bus stop, which is on the far side, located on the far side of the intersection. So, 0.5 has been used. Curb lane capacity, curb lane volume we know, we can develop curb lane capacity. Traffic blockage adjustment factor, again these are standard values that can be calculated or that is usually given to you. What is a traffic blockage adjustment factor? Again, it depends upon whether the queuing buses are blocking the traffic behind them, right. So, if the loading areas, they are not able to get into the loading areas, they are queued up and they are queued up into the traffic lane. So, then the traffic is not able to move. So, that is the traffic blockage adjustment factor. So, if you know certain if you know these standard values, this one standard value in this case and this one from the table right here, you can calculate the bus stop capacity. The bus stop capacity is given by a multiplication of these 3 factors. NEL, NEL is the number of effective loading areas, you already know that. FTB, FTB is the traffic blockage factor standard, we have already calculated that, and BL, BL is given by this factor which you have already calculated in the previous step, that is the loading area design capacity. Loading area design capacity we already just calculated here. So, that is the same one here. So, you may develop the bus stop capacity. So, now you know that this stop number 1 can process 47 buses per hour, whereas stop number 2 can only process 36 buses per hour. So, that gives you the understanding of how your bus stops are able to handle your bus frequency that you have scheduled for the entire route, right. So, that is an example of bus stop capacity. Similarly, we will go through quickly an example of how to calculate the capacity of a rail transit line. In order to do so, what you need to know is the minimum train separation, the controlling headway, because headway, remember headway is what determines usually what capacity your trains are running at, and the resultant line and person capacity. So, line capacity is different than person capacity, because line capacity meaning how many train coaches you have, and in one line how many trains run every hour. So, that gives you the entire line capacity, whereas person capacity is how many people actually are running on the line, whether there are fewer than line capacity or more than line capacity or coach capacity. So, all that gives you the capacity of your transit rail line. So, in case of metro line or suburban train line, if you want to calculate, mostly for heavy rail transit line, right. So, if you first one, if you again similarly will go through different input parameters. Minimum train separation, if you want to calculate, there are a lot of parameters that you need to get into. You can look at each of these. We have already given you the reference link at the end of the presentation. All of these solved problems are solved there as well. So, go through that. Similarly, you already know the concept by which we are telling you how to calculate these. Given sets of parameters will be there, their default values will be there. All you need to do is take the empirical formula. You need to know which empirical formula to pick, which of the variables, which of the constant values to pick, and you have to pick them, insert them into the right formula in order to get the answer. So, understand all of these quickly. Longest train length you have to know, maximum line speed you have to know, approach speed, right. For similarly, the others, acceleration, deceleration speed, braking time, whether the station is at grade or is there any incline or decline into the station. So, all of these values are given here for different types of signaling systems, right. This is something that is that you have to determine what type of control system you have for your rail line, and for different types of systems there will be different parameter values that will be that you would need to insert. So, again these parameter specific control systems are given here. Safety factors for this type of control system, the value is this much, whereas for a cab signal type the value is this much. So, you need to know which one to pick based on what you have, what type of system you are developing, and finally, the minimum train control separation is what you are trying to find out, and it is given by this empirical formula. Like I said again, in the case of bus, do not get intimidated by the length of the formula, they are not very complex. Each of those values are already, the values have already been given as input parameters. Just go through each of these each of these input parameters here, and also the input parameters here, these you have to calculate, but these input parameters right here, insert them for each type of control system. So, this is one type, this is the other type. So, insert the parameters as per the control systems, and you will calculate what is called a minimum train control separation. Once you know the minimum train control separation, the next step or the second problem, if you remember, now you have calculated minimum train control separation. The next is controlling headway. Now, in order to calculate controlling headway, first you need to calculate what is called a non-interference headway. Non-interference headway is very simple. It is just the addition of 3 different times: the train control separation time, which you just calculated, average dwelling time for at control stations, again standard values that will be given, and operating margins. Operating margins again will be given. So, this is something that you just calculated. So, you see these are imported inputs, that means imported from the calculation that you have already done, and you just add these 3 to get this value. So, that is non-interference headway. The second headway that you need to calculate is the minimum headway with respect to right of way type, right. If it is a exclusive right of way, single track, on street, private right of way, or grade separated. So, 4 different types of right of ways will have different capacities. Remember, if it is a grade separated private right of way, that has the highest capacity, whereas if it is on street, it is mingling with other types of vehicles, it has a lower capacity. So, all of that will depend upon, again there are a bunch of inputs that you could go through, and finally, what calculations you have to do is, first you have to determine the time to cover single track station, minimum single track headway, minimum on street section, that will give you the non-interference headway associated with stations at with grade crossings at on departure, and finally minimum headway associated with right of way type, which is the nothing but the maximum of HST that you have already calculated, HOS here and HGC here. So, out of these three, whichever is the maximum, that will be the minimum headway associated with the right of way type. Okay. Again, do not get carried away by the length and complexity of the formulas. All input parameters have already been given to you. Just input those parameters into the formula. What you need to understand is what each of the elements in the formulas talk about, right. You have to know what is Tij, you have to know what is TBR and why they are affecting the calculation of controlling headway, why they are affecting that. If you understand that, and that should be easy to understand. Finally, you have to calculate the limiting headway. The third type of headway that you need to calculate is the limiting headway, and the limiting headway at the junction is calculated by this formula right here. You already have most of the input parameters that you have calculated in the previous ones. The only inputs that you will need here is the track separation feet, how much your track separation right of way is separated from the grade, it is at grade or not at grade, and then the switch throw and lock time. These are again standard values that will be given to you in a tabular fashion, or they are standard in a book that has all the standards. All you need to do is look for the right value. So, that is what you have to do. Calculations, switch angle factor again is something that you have to be looking for. These are again standard values. You input all of these values in this formula and you get the limiting headway. So, now the controlling headway is the maximum of these three headways that you have just calculated. See, imported inputs, you have calculated the non-interference headway, you have calculated the headway imposed by right of way types, and you have calculated the highest limiting headway at a junction. The maximum value among these three will be your controlling headway. So, once you know the controlling headway or the headway value is 376, you have calculated the controlling headway. Now, you can go ahead and calculate the line capacity and the person capacity. In order to do so, first you have to determine whether there is any layover time at the terminal. That layover time at the terminal, it should be less than or equal to this entire formula. Again, all of these are input values that are either given here or already has been given earlier in solving these problems. Input this. If it is not less than or equal to that, then use the value that you get here. It has to be at least less than or equal to the right hand side value. So, that is what terminal layover time is telling you. Calculations shows that the terminal layover time is 178 here. With that terminal layover time and controlling headway that you have already calculated, the line capacity is given by this formula and the person capacity is given by this formula. You already know the line capacity, number of trains per car, maximum design load, number of persons per car, and the peak hour factor. If you know all of that, person capacity is 1. So, your transit line can carry 8,640 persons per hour, and this one if you have used different way, if you have used for a different control system. So, this is a parallel, you know, remember the different control systems that we were talking about. If there is a different type of a control system that you have carried out all these calculations for, the capacity would be different. So, basically it depends upon which type of control system you are using for the train, will tell you what capacity your train is running at, what the headway between the trains are, what is the controlling headway, meaning which is the maximum of the three headways. That headway will also control how much is the capacity of your transit line. So, this is the reference that we were talking about and all of these examples are solved in that reference. So, please look at it carefully. The calculations may seem complex, but they are not at all. They are empirical formulas. Input values will be always given to you, standardized values will be available in standard tables. All you need to do is pick the right value from the tables and pick the correct formula for calculating these values. So, in conclusion, we have explained to you in detail how to calculate the capacity of your bus transit line and also your capacity of your rail transit line, what those capacities depend upon. Bus capacity maybe depends upon your loading areas, number of loading not only number of loading areas, but also loading area capacity, which may in turn depend upon the dwell time. Similarly, in case of transit, rail transit, you saw that the headway, the controlling headway is something that will affect your line capacity as well as person capacity. So, understanding these terminologies and these factors is very important in determining the line capacity, determine the capacities of your bus and transit line. Thank you very much for your attention.